This is Chapter 14, Section 1, Aldehydes and Ketones. One place you might have heard of aldehydes before is in the compound formaldehyde. You can see in this picture how a solution of formaldehyde, known as formalin, is used to preserve biological specimens because it acts as a germicide. But you probably know it better as the principal component of embalming fluid, which is used to preserve bodies after death. So aldehydes and ketones are both compounds that contain what's known as a carbonyl group, a carbon double bonded to an oxygen. In this section, we're going to learn about the similarities and the differences between these compounds and their structure, as well as how to write the IUPAC names for both of them and how to draw their condensed and line angle structural formulas. As I said, both of these compounds contain the carbonyl group. This is a carbon attached to an oxygen through a double bond. And so you can see it present here in this structure and here in this structure. The difference between an aldehyde and a ketone is in where the carbonyl carbon is. In an aldehyde, the carbonyl is always a terminal carbon, which means that one of the other bonds going to the carbonyl carbon must be a hydrogen. In a ketone, it's an interior internal carbon that has the carbonyl group, and so both of the other bonds going to that carbon have to be to other carbons, possibly part of longer chains. Since the carbonyl carbon is attached to two other atoms and then double bonded to an oxygen, it has three atoms bonded to it, no lone pairs, which gives it a trigonal planar geometry with angles of 120 degrees. The carbonyl group is interesting for a few reasons. One of them is due to its polarity, which causes a certain kind of reactivity. So the oxygen in the carbonyl group pulls electron density towards itself more efficiently because it's more electronegative, and so that leaves a partially negative charge at the oxygen side and a partially positive charge at the carbon side. The polarity of this carbonyl group gives compounds containing this group many characteristic properties, both physical and chemical. In the IUPAC system, aldehydes are named by replacing the E at the end of the parent alkane chain with an AL ending for aldehyde. The carbon in the aldehyde group is always counted as carbon number 1 because it has to be a terminal or end carbon. However, since it's always number 1, we can drop it. We don't need to include the number 1 in the name, and it's really only used to count the chain in case there are other substituents that need to be numbered. This makes the naming of simple aldehydes relatively easy. You just find the name of the carbon chain that the aldehyde group is on, and you replace the ending with Al. So, for instance, if we have one carbon, that would be methane. If there's a carbonyl group on that single carbon, then instead of methane, we have methanal. Again, we're not interested in the common names, so we can cross all those out so that we don't get confused. We have methanol. For this first one, this is actually the compound which is more commonly known as formaldehyde, but the proper IUPAC name is methanal. If the carbonyl carbon is part of a two-carbon chain, then ethane becomes ethanal. If it's part of a three-carbon chain, then that would be propane, so we change the name propane to propanol. And if it's a four-carbon chain, it becomes butanol. Keep in mind that the carbonyl carbon is counted as part of the chain. It's tempting sometimes to look at this and think that you have an aldehyde group attached to a one-carbon chain here, but this carbon is part of the chain. So this is not, in fact, a one-carbon chain. It's a two-carbon chain. There's also a special case of an aldehyde attached to a benzene ring, which in the IUPAC system is called Benzaldehyde, and you can see the structure for Benzaldehyde here. Again, if there are other substituents, we would number this as the one carbon and then count the shortest distance to the other substituents to get the number for that. But the number 1 for the aldehyde substituent in the benzene ring is never needed. So let's look at this example. Give the IUPAC name of the following structure. We have a carbonyl carbon with an H attached to it, and that makes this an aldehyde group. We have to count that carbonyl carbon as carbon number 1, and then we can count from there. This one is 2, this one is 3, this one is 4, and this one is 5. We also have this methyl group on the third carbon, so our prefix is 3-methyl. And then it's a 5-carbon chain with an aldehyde. So pentane, you drop the E and it becomes pentanol or pentanal. With ketones, you generally do need to include the number, although in some of the simpler cases you don't. So again, I'm going to start by crossing out the common names so that we don't get confused with those. But what we still need to do is find the longest carbon chain that has the carbonyl carbon in it, and then name that. Drop the E at the end of that alkane name and replace it with ONE for the ketone. And then in some cases, we will have to number it. In most cases, we'll have to number it. Here you see a few examples where a number is not necessary. And that's because of the distinction between ketones and aldehydes. So for instance, this example, you have a 3-carbon chain with the carbonyl group in the middle. A 3-carbon chain is propane. Since this is obviously a ketone, we call this propanone. But why don't we need the 2 to indicate that the carbonyl group is on the second carbon? Well, that's because if we had a 3-carbon chain and we put the carbonyl carbon on an end carbon, that would no longer be a ketone. It would be an aldehyde. And so there is no ketone where the carbonyl group is on the first carbon or the last carbon. It has to be on one of the internal carbons. Since there's only one internal carbon in propane, there's only one possible place to put the carbonyl to make propane into a ketone. The same thing is true of butanone. It seems at first like we have a choice between 2 different carbons, but in reality these would give us the same answer, just rotated 180 degrees. So there's only one potential internal carbon that we can place the ketone on to get butanone. For pentanone, however, we do need to start numbering. So you can see here you have a 5-carbon chain, and in this case the carbonyl carbon is in the very center. So it doesn't matter which side you begin counting on because they're both the same distance from that carbonyl. So we can start here with this carbon is number 1, this would be number 2, and then the carbon in the carbonyl is carbon number 3. And that's why this is called 3-pentanone. 2-pentanone would be if the carbonyl group were on this carbon instead. And that would still be a ketone because it would still be connected to carbons on either side. But we can't put the carbonyl here and call it a ketone. In that case, it would be an aldehyde. So the only possibilities with pentanone are 2-pentanone, which is with the carbonyl here, or 3-pentanone, which is what's been drawn here. For cyclic ketones, you would simply place the cyclo prefix at the beginning of the ketone name. And here again, if you have a cyclic ketone, the carbon where the carbonyl group is would be carbon number 1, and then you would count the shortest distance to any other substituents. If there are no other substituents, you don't need to know the number 1. You don't need to give the number 1. So in this example, we have a 5-carbon ring, which is cyclopentane. With the carbonyl group as one of those carbons, it becomes cyclopentanone. Note that it couldn't really be a cyclic aldehyde in the same way because the aldehyde must be a terminal carbon. In this example here, we have cyclohexane. With the carbonyl group, it becomes cyclohexanone. And then we can start the numbering system. So you would count the carbonyl carbon as number 1, 2, 3. So this methyl group here is on the 3rd carbon, and it becomes 3-methyl cyclohexanone. You'll see there's still no need to put the number 1 for the placement of the ketone. You can leave that out entirely. It's just 3-methyl cyclohexanone. So here we can see an example of a ketone. The carbonyl carbon is here with carbons on either side of it. So we have to find the longest chain and then figure out the correct counting system. So the longest chain is clearly just this one, which is 5 carbons long. So this is a pentane derivative. The carbonyl carbon is here, which is closest to this end. So this would be carbon number 1. And then this would be carbon 2. This would be 3. This would be 4. And this would be 5. So we have a ketone with the carbonyl on the 2nd carbon. And we have a methyl on the 4th carbon. So this is going to be 4-methyl dash 2 dash pentanone. Pentan because it's 5 carbons long, the 2 because the carbonyl is on the 2 carbon, and 4-methyl because that's where the methyl substituent is. So 4-methyl 2-pentanone. So I mentioned before that formaldehyde is used as a biological preservative as well as in embalming fluid, but it's also used in a lot of industrial processes like making synthetic polymer fibers into fabrics, insulation materials, carpeting, plywood, plastics for kitchen counters and appliances. But it is a toxic chemical, and exposure to formaldehyde over extended periods can cause irritation to the eye, nose, and throats, your respiratory tract, skin rashes, headaches, dizziness, all sorts of complications. The simplest ketone is formally known as propanone, but the more common name you've probably heard is acetone. And in fact, it's in such common usage that IUPAC allows acetone as the official name as well. Place you've probably seen this would be in nail polish removers, which you could find at your local pharmacy, but it's also present in rubber cement, solvents, and cleaning fluids and things of that nature. Your body does sometimes produce acetone, usually during situations where you have dysregulation of metabolism. For instance, if you have uncontrolled diabetes, or if you are in a high protein diet and you're metabolizing large amounts of meat fats and things like that. Some naturally occurring aromatic aldehydes are used as flavoring agents in foods or fragrances and perfumes. For instance, benzaldehyde is found in almonds. This structure is vanillin, which we already saw as an example of a phenol, but it also has an aldehyde group attached to the benzene ring, so it's a benzaldehyde as well. Also has an oxygen bridge here, so it's really an ether too. It contains a few different functional groups. In this example, we have a derivative of cinnamon, cinnamaldehyde, which contains the aldehyde group attached through a double bond to the benzene ring. So here are several examples of aldehydes or ketones. So let's figure out which they are so that we can name these. In this first example, A, you have this structure here, which is CHO. Now, this is a condensed way of writing an aldehyde. You might confuse it at first for an alcohol group, an OH group attached to the carbon. But if you look at it, you can see that that carbon, if it were just attached to an OH group, would really only have two bonds going to it. Okay, it would have the bond to the rest of the carbon chain and then the bond to the OH group, but there would be nothing else indicating what it should be attached through the third and fourth bonds. So that is an incorrect interpretation of that condensed structure. It can't behave that way. Instead, the carbon, which is attached to the rest of the chain through this single bond, must be double bonded to an oxygen, and then the last bond, the fourth bond, would be single bonded to that hydrogen. So this is the correct interpretation of the CHO condensed formula, and this is clearly an aldehyde group. So we can name this as an aldehyde. We just have to count the chain. This would be the first carbon in the aldehyde group. This would be number 2, this would be 3, and this would be 4. So that would make this a butane derivative. Again, we just drop the E and make it butanol. We see something similar here. This is the oxygen-containing functional group that we're interested in. It looks like it could be an ether, but again, you have the single bond to a carbon, and if that's just bonded to an oxygen, which is then bonded to the rest of the molecule, this carbon doesn't have the correct number of bonds going to it. So this cannot be the correct interpretation of that structural unit. Instead, the carbon is single bonded to the rest of the carbon chain, and it must be double bonded to the oxygen and then single bonded to the rest of the chain on the other side. And that makes this a carbonyl group on an internal carbon, which makes this a ketone. So now we just need to count the chain and then find the position of the ketone. So we can start at this end with this is carbon number 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So it's hexane. If I started the numbering from the other end, I would find that the carbonyl is on the 4th carbon. So I wouldn't want to do that. I want to choose the numbering system that gives me the lowest number for the carbonyl. So that's carbonyl on carbon number 3. And so that makes this 3-hexanone. We just dropped the E and replaced it with ONE for the ketone. Here we have a cyclic ketone. It should be pretty evident from this structure that we're dealing with a ketone. It has a 5-membered ring, which would be called cyclopentane. But as a ketone, we drop the E and we replace the E with ONE as the ending. cyclopentanone. In the last example, we have another aldehyde here. Hopefully you can see that this carbonyl carbon is directly bonded to an H, so it's a terminal carbon. That's what makes this an aldehyde. So that carbon would be number 1, this would be number 2, this would be number 3, and this would be number 4. And so this would be an alternate way of drawing butanol, which we saw in A. Here are a couple of more examples. In this first one, we have that CHO functional group again, which makes this an aldehyde, but now we also have a chloro substituent. So the aldehyde carbon is number 1, this would be 2, this would be 3, this would be 4, and this would be 5, which makes this pentanol, but the chloro group is on the 4th carbon, so we can call it 4-chloropentanol. In this example, we have to recognize that the aldehyde group is attached to a benzene ring, so it's this entire structure that gets formally named as benzaldehyde, and then this is a substituent on the benzaldehyde. It's a 2-carbon chain, so this is really an ethyl group, and it's attached to the 2nd carbon. The carbon where the aldehyde is attached is number 1, and then this is called carbon number 2. So this would be 2-ethyl benzaldehyde. Now let's do a few examples of drawing the structure from the name. This question says to draw the structure of 3-ethyl cyclopentanone. So we know we're looking for a ketone that's going to have a carbonyl group, and we know that it's going to be part of a 5-carbon chain. But the cyclo here tells us that it's a 5-carbon ring, actually, so we should start by drawing cyclopentane. Then we can add the ketone, the carbonyl, anywhere on the chain, so here's a good place to put it, and that would make this carbon number 1. And then we can number in either direction since we're making the structure, so I can call this number 2 and this number 3, and that's where my ethyl group would go. In a line angle structure, ethyl just looks like that. Get rid of my numbering system, and there you have the structure for 3-ethyl cyclopentanone. Here are 3 more examples. A is 2-bromopentanol. So we know that the Al ending means that this is an aldehyde. There's no cyclo, so it's an open chain with pent or 5 carbons. And so we can write this as 1, 2, 3, 4, 5 carbons. Put in our single bonds. The terminal carbon is going to have an aldehyde group, so I can make that this carbon with a double bond to an oxygen and then a bond to a hydrogen. That gives you my aldehyde at the 1st carbon. And then the bromine is going to be on the 2nd carbon. So if this is carbon number 1, then this is carbon number 2, where the bromine is. And then all I have to do is fill in the remaining hydrogens. This carbonyl carbon doesn't need any more, so I can just fix that bond between them, make it a little nicer. This carbon with the bromine on it has 3 bonds already, so it just needs 1 more hydrogen. This carbon has 2, so it needs 2 more. This one also needs 2 more, and the final one needs 3. And so this is 2-bromopentanol. If I wanted to draw this for a line angle formula, I could just draw a zigzag. 1, 2, 3, 4, 5. That's 5 carbons. Put the carbonyl carbon on the end. I can draw the hydrogen bond in if I want to, or leave it out if I don't. Either way is fine. And then we can put the bromine on the 2nd carbon, which would be here in this case. And then we don't need to worry about anything else, because for a line angle formula, you don't need to draw any hydrogens in explicitly. So this would be the end of the line angle formula. Either one would usually be acceptable. For B, you have 3-methylbutanone. So here you have a butane chain, so let's start with a 4-carbon chain. And you need to make this a ketone. But you'll notice that there's no number for the ketone, right? We know that there's a methyl group on the 3rd carbon, so I could count, say, I assume counting left to right, 1, 2, 3, so this would be a methyl group here. But where do I put the ketone? Well, I can't put it on the end because then it wouldn't be a ketone, it would be an aldehyde. And I can't put it on the third carbon because then once I connect these all, I would have too many bonds on that carbon. And also, if I did that, then the carbonyl carbon would really be number 2 because I would start counting from this end and that would be 2. So that would make this 2-methylbutanone. So what we find is that 2-methylbutanone doesn't really exist because it implies that the ketone and the methyl are on the same carbon, which they can't be. But 3-methylbutanone means that the only place I can put this ketone group is here on this carbon. It's the only place that has space available for a carbonyl on an internal carbon. And so then we can just finish everything else. This is CH3. This carbon does need one more hydrogen, so that's CH. This is going to be completed with the double bond and the 2 bonds to the rest of the chain, so no more hydrogens there. And then this terminal carbon is going to need 3 hydrogens as well. So this is our structure of 3-methylbutanone. Even though there's no number for the ketone, there's only one place that you can put it. For C, we have 3,3-dimethylbutanol. So we have an aldehyde with 4 carbons. So we can start with our 4 carbons again. Put the aldehyde on the very first carbon with the hydrogen, since I'm drawing a condensed structural formula. And then I need to find the third carbon so I can put 2 methyl groups on that, right? Dimethyl, and the number for both methyl is 3. So if this is 1, this is 2, this is 3. So this is going to have 2 methyl groups on it. And just to give it room, I can place one pointing up and one pointing down. And then that's it. I can just finish everything else by bonding that carbonyl group. This would require 2 hydrogens, this would require no more hydrogens, and this would require 3 hydrogens. And so this is the structure for 3,3-dimethylbutanol.